Alright, hello everybody, welcome back. This is video number 2 in Unit 1, Section 8 of AP Calculus, determining limits using the Squeeze Theorem. In this video, we're going to develop a couple of important rules using the Squeeze Theorem, some important limits that we'd like to kind of know, and then we'll look at a few examples of how we can use the most common of those. In order to help us find some limits involving trigonometric functions that we did not previously have a method for finding. Alright, so we're going to find two limits. We're going to find the limit as x goes to 0 of sine of x over x, and we're going to find the limit as x goes to 0 of 1 minus cosine of x over x. We're also going to talk about the limit as x goes to 0 of x over sine of x. But we're going to find these first two using the Squeeze Theorem. So here we go. Let's start with the limit as x goes to 0 of sine of x over x. And if you were trying to do this from scratch, we would use some areas and some trigonometry and develop these relationships, but it's not worth our time to take all the time to do that and develop these relationships. But basically, we would be developing these two relationships that you see here, that sine of x is less than or equal to x is less than or equal to tangent of x, and that cosine of x is less than or equal to sine of x over x, for all the x values between negative pi over 2 and pi over 2. Okay? Now realize what we're trying to do is we're trying to sandwich in sine of x over x. And if we use this relationship right here, we immediately have that cosine of x is less than or equal to sine of x over x. So all we need is the right-hand side of our squeeze inequality. We need some function that sine of x over x is always less than or equal to, and we're going to get that from this relationship right here. If we take this relationship right here and divide everything by x, it becomes the relationship sine of x over x is less than or equal to 1, which is less than or equal to tangent of x over x. Okay, and we're going to use the fact that sine of x over x is less than or equal to 1. And that gives us this sandwich relationship right here. Okay, we're squeezing it in. And now all we need to do is we need to find the limit as x goes to 0 of cosine of x. We substitute 0 into the cosine function, and we get that that is 1. And of course, the limit as x goes to 0 of 1 is just 1. So sine of x over x is in between cosine of x and 1. Both of those have a limit of 1. Therefore, by the Squeeze Theorem, we now know that the limit as x goes to 0 of sine of x over x is equal to 1. Okay? Next, let's find the limit for 1 minus cosine of x over x, using some things that we learned in our previous lessons. And guess what? We're not even going to need the Squeeze Theorem to do this. We're just going to need the result that we just got in order to do this. So first of all, let's check out what's going on here. The limit as x goes to 0 of 1 minus cosine of x over x. If you try to substitute in, cosine of 0 is 1, and so this leads to a situation where we have the indeterminate form 0 over 0. So we're going to try and simplify this algebraically. And we need to try and turn that numerator into something where we can make a substitution that, works to our benefit. So what I'm going to do is I'm going to multiply both numerator and denominator here by the quantity 1 plus cosine of x. which turns this limit into the limit as x goes to 0 of 1 minus cosine squared of x all over x times the quantity, x times the quantity 1 plus cosine of x. Now we go back to that Pythagorean identity that everybody knows and loves. Sine squared of x plus cosine squared of x is equal to 1. If we subtract cosine squared from both sides, we see that 1 minus cosine squared of x, which is what we have right here, is equal to sine squared of x. And so I'm going to go ahead and make that replacement. And so this becomes the limit as x goes to 0 of sine squared of x over x times the quantity 1 plus cosine of x. Using limit properties that we already know, we know that the product of two limits is the limit of their product. And so what we can do is we can split this limit into the product of two separate limits. And I'm just going to split these things up. The limit as x goes to 0, and I'm going to take one of the signs from the numerator and the x from the denominator in one limit. And in the other limit, I'm going to take the other sign from the numerator and the quantity 1 plus cosine of x from the denominator. And now I can calculate these limits. This limit right here, we just found in our previous using the squeeze theorem. That limit is 1. And then the limit as x approaches 0 of sine of x over 1 plus cosine of x, we can just do via substitution. The sine of 0 is 0. The cosine of 0 is 1, and so that becomes 0 over 2, and 1 times 0 is indeed 0. And so that's the value of the limit as x goes to 0 of the quantity 1 minus cosine of x over x. And so let's put these here. We found this limit. We found this limit. Now if we know the limit as x goes to 0 of sine of x over x is equal to 1, the limit of some function's reciprocal, if you remember limit properties, we had the power property that the limit of a function raised to a power is equal to the limit raised to that power. So this is just the limit of sine of x over x to the -1 power. And so this is just going to be 1 to the -1 power. In other words, the reciprocal of 1, and so that's also going to be 1. And so anytime we have a limit as x goes to 0 and we can break out a sine of x over x or an x over sine of x, we can replace that as a 1. And anytime we are breaking down a limit and we can break out a limit as x goes to 0 of 1 minus cosine of x over x, we can break that out as a 0. All right. Now, of course, these first two we're going to use a lot more than the third, in my opinion and in my experience. Let's look at how we can use some of these in context and how they might work. So let's look at example 4a here. Limit as x goes to 0 of the sine of 4x over x. Now in order for this rule to work, what's inside the sine function has to be the same as what's in the denominator. And those things have to be approaching 0. So in order to find this limit, I want to change this denominator so that it is the same as what's inside of the sine function. Well, how do I do that? Well, I'm just going to go ahead and multiply that denominator by 4. If I multiply that denominator by 4, I must also multiply the numerator by 4. And so this is now equal to the limit as x goes to 0 of 4 sine of 4x over 4x. Since this right here, as x goes to 0, 4x is going to go to 0. That's just going to be 1 as the limit. What I'm going to do is I'm going to take that constant 4 right here, and I'm going to bring it out in front of the limit. And now I know that this limit is 1, and so the value of our limit here is going to be 4. Okay. Let's look at part B here. We're going to split our denominator. Got the limit as x goes to 0. And again, in all of these cases, these are indeterminate forms. If I tried to substitute 0 in for the limit in part A, it would be a 0 over 0 form. Same thing in part B. If I substituted 0 into the numerator, it gives me 0. 0 into the denominator gives me 0. So, all right, let's see. I can factor this denominator. I can factor out an x. And now I can split this just like when we were developing the limit rule up at the top of the page. We can split this into two limits. The limit as x goes to 0 of sine of x over x times the limit as x goes to 0 of 1 over 2 minus x. And if I multiply those two limits together, I get the limit that's up on the line above. And so now I'm going to take each of these limits. We know that the limit as x goes to 0 of sine of x over x is 1. And when I substitute 0 in here, it gives us 1/2, and so this value is 1/2. For all the time that I've been teaching AP Calculus, I always told my students that I wanted us to be able to develop everything, but that there was one thing that I would recommend that they had, memorized off the top of their head, and that was that the limit as x goes to 0 of sine of x over x was equal to 1. All right, let's look at example C. Limit as x goes to 0 of 3 tangent of 7x over 5 sine of 4x. And we're going to find the value of this. The first thing I'm going to do is I'm going to turn that tangent of 7x into sine over cosine, which turns this problem into 3 sine of 7x over 5 cosine of 7x sine of 4x. Okay. And now what I'm going to do is I'm going to kind of collect my terms here and decide exactly how I want to do this. The first thing I'm going to do is I'm going to go ahead and take the 3 and the 5 and bring them out in front of the limit as constant multiples. And then I'm going to turn this limit into a product of a few things. I'm going to write one term where sine of x is, or sine of 7x is in the numerator. I'm going to write one term where cosine of 7x is in the denominator. I'm going to write one, I guess I should be saying factor, and one factor where sine of 4x is in the denominator. And then I'm going to have a fourth fraction out here to put everything in that I add into these expressions. Now ideally, if I have sine of 7x over 7x, I know the limit of that is going to be 1. So I'm going to put a 7x in this denominator, which means I need a 7x in this numerator. I'm going to go to the third fraction. I need the numerator of the third fraction to be the same as what's inside of the sine function. So if I put a 4x in here, then I also need a 4x in the denominator of my collection term here. And lastly, I don't have a rule for anything over cosine of 7x, and if I try and take the limit of that as x goes to 0, I can just substitute 0 in. So I'm just going to make this numerator 1, and I don't need anything in my compensation factor then. So look at what happens here. The x's in the 7x over 4x cancel out, so I can bring the 7/4 out in front, and this becomes 21 over 20, times limit as x goes to 0 of sine of 7x over 7x times limit as x goes to 0 of 1 over cosine of 7x times limit as x goes to 0 of 4x over sine of 4x. And every single one of these limits inside of my brackets here have a limit of 1. And so my final answer for my limit here is 21 over 20. All right, running up right against the time limit here. That takes us to the end of this video and the end of our lesson on the squeeze theorem. See you folks next time when we do section 1.9 of Unit 1, connecting multiple representations of limits. See you then. Have a great rest of your day.